Thank you, David, and also thank you, Andre, for organizing this this wonderful event. I think it's fantastic to see all these talks this week. Indeed, I changed the title of my presentation, I think about a week ago, to column elimination as an alternative to column generation. I hope you like it, and I hope you understand why I positioned the work like this. It's actually more about a new way to solve problems that would otherwise be solved with column generation, and possibly more efficiently with decision diagrams now. I would like to call out, this is joint work with Zia Tang and Anthony Karahelios, parts of it at least. Zia graduated from our PhD program early this spring this year, and Anthony is a current PhD student. So let me get started with my plan here. We have about 1 hour. I hope it fits. I have ways to speed up if needed. I would like to give you some opportunity to ask questions whenever possible. So we'll see where we get. Since I really want to contrast column generation to this new idea of column elimination with decision diagrams, I would like to start with giving you a brief introduction to column generation. I understand many of you have an optimization background. It will be a recap, but it would be good to set our minds what we would like to establish with decision diagrams here. And the first example will be graph coloring that will allow me to both highlight what column generation is and then how to do the same thing or similar things in decision diagrams, and then contrast the two. Then we'll move into a more complex application in the context of vehicle routing, the traveling salesman problem with a drone. And then I'll look into more structural connections between the bounds we get from decision diagrams and those from column generation. But that's the plan, and we'll start with graph coloring, and then we'll move from there. So I'll just work my way from this example first. Graph coloring is a very fundamental application of combinatorial optimization. It's very widely applied as a subproblem, or the only problem sometimes, in scheduling applications, rostering applications, and so forth. And it has been studied computationally and theoretically for decades, over 100 years at least. Exact methods exist. The state of the art is either very dedicated methods or typically based on column generation or integer programming. A challenge for exact methods is to find good lower bounds. And I now realize that I skipped the definition of graph coloring. So let me just briefly give you that definition. We have an input graph here with 4 nodes and edges, and the coloring of this graph is a color to each vertex so that adjacent vertices or nodes do not get the same color. And here's an example of 2 colors, the blue and the green color, and they have there's no edge in which the endpoints have the same color. So we need to find a feasible coloring with the minimum number of colors. And that's been really a very interesting challenge. And if you look at the computational literature, there's more people now getting into this domain again, but there's not as many papers on graph coloring as there are, for example, on traveling salesman problems or on vehicle routing, for example. So this remains a very, very challenging application. So if you want to think about a MIP formulation to solving this problem, your first attempt would be probably your default approach would be, let's try to identify a variable y for vertex I in color k, indicating a binary variable that you color vertex I with color k. It's the obvious first attempt, I would say. And then you have to just make sure that neighboring nodes do not get the same color. So if you have 2 nodes I and j, they cannot be assigned the same color using this linear constraint. This was one stream of literature that can actually be quite effective. And on some graph coloring benchmark instances, this can really be state of the art. They would close these instances that perhaps column generation may not be able to close, or get very strong bounds. So this is not necessarily a very bad attempt, but as is, just like this, it gives you quite weak LP relaxation. If you want to improve on this, you need to have other cuts, for example, strengthening formulations to make this work. An alternative formulation would be a column generation approach, or a more explicit formulation that is the following. It was originally introduced by Mirotra and Trick in 1998, I believe it was. And the idea was here to not look at the individual nodes and give them a color, but look at sets of nodes and color them all at once. And that will be a color class. For example, in this particular graph, we have different color classes, and the one is the solution here, 1, 4, and 2, 3, are 2 separate color classes that together cover all the nodes. So the idea of this MIP formulation is to enumerate all possible feasible color classes, and I list them here. And the empty set I omit because it's not really needed for our for finding a solution here. So these are all possible color classes that do not have any edges in common. These are the independent sets of the problem. And I understand from Andre that you have seen independent set decision diagrams yesterday as well. So this should be familiar with you to you. And then if we have all possible independent sets and color classes, the choice now is which of these will we pick the minimum number in fact, so that we color all the nodes. And every node is, of course, part of one of these color classes. And this is a standard set partitioning formulation for graph coloring in this case. Now we'll see in the next application, the routing application, almost exactly the same. I think it's literally the same formulation, only I changed the J, the index J to be R for root, because this is always, it's very often the same set partitioning formulation for all these column generation approaches. The benefit here is we have a stronger LP relaxation, and we can oftentimes compute this quite quickly as well. So let me show you how you would get the column generation going to build this model, because clearly the set of all independent sets is exponentially large. So we typically start with an initial subset, a restricted set of columns. For example, we can select, and we have to ensure feasibility. So when you first start solving this with a linear program, you need to make sure there is at least one feasible solution. So maybe we can give every vertex or node its own color. And that means we would have just 1, 2, 3, and 4 as the separate color classes. We would need 4 colors to color this. We have a very simple initial LP, and we solve this LP. This is the set partitioning LP. If we find that the solution here of 4 colors, clearly, we get some shadow prices, 1 for each constraint, for each node, that it be covered. And in this particular case, all the shadow prices are 1. Now we ask the pricing problem, is there another column, another variable, another independent set that if we add it to our formulation, that would decrease now the objective function? For that, we need to have a negative reduced cost. So it depends on the shadow prices we get from the master problem. Here's a definition. The pricing problem asks to find a new independent set. So an independent set is a subset of nodes. We have a binary variable, 1 associated with each of the nodes here. And we need to pick a subset of the nodes that are not having any edges in between them. So the constraints that we have here make sure, for example, 1 and 3 are both not picked in our independent set. So give me any new subset of nodes that gives me an independent set, and it has a negative, in fact, a minimum reduced cost. So let's do that here, and we'll find a new independent set, 1 and 2. That's a new subset. We add it to the master LP as X5. We resolve the LP, we get new shadow prices. We go back to the pricing problem. We find yet another independent set, 1, 4, which is also an independent set. We add it to the LP. We resolve this. We get a new pricing problem. We get a new independent set, 2, 3. And now if we solve this LP, we get an optimal solution of 2 in the LP. We get a reduced cost of 0 in the pricing problem, which means there's no more negative reduced cost variable available to us, and then we can terminate. And we have proof by LP, a theory that this is actually the optimal solution. There is no more other variable that we can add to the basis that would improve further this solution. So that's how column generation works. And I wanted to show you this because it very nicely visually shows that you add column or variable after variable after variable. But in the end, what you need is an optimal basis, right? In this case, X6 and X7 are sufficient. If we had started with X6 and X7, those two, we would not have been able to find any other column to add to this, and we would be terminating much more quickly, okay? So this works fine. I use column generation all the time if I can. It's a very powerful method, but this is not sufficient. It is just giving you an optimal LP. It could be, in this case, we saw, of course, we had an optimal integer solution because it's so simple. But normally you get a fractional solution and you have to embed it into a branch and price. This is not very straightforward. And in many cases, you have to be very careful in how to do the branching. In this case, you can say 2 nodes get the same color or they don't get the same color. And these branching constraints have to be reflected in the pricing problem. This works quite well in this case for graph coloring, fortunately. And for routing, for example, you can do similar branching constraints. But this is still an issue. And what is, for me, as I use it in practice, sometimes an issue, and I found this actually for larger applications, they don't get a valid lower bound until you find the optimal basis in your master. And that can take hours or hours and hours. And that's really a drawback because I want to have good bounds early on in a branch and bound process. It's very difficult for me now to trade off my branching and my computation of the bounds if it takes me hours to even compute an optimal basis in the master problem. There's other issues like stability, convergence issues because of degeneracy of the LP, but let me just go over that. So as an alternative, why don't we look at in column generation, the restricted set of columns that do not give us a valid bound? Why don't we look at a relaxed set of columns that has more than only the feasible set of columns? That will always give us a valid bound. And that's what we're going to propose here. And now to get that bound tighter and tighter, the idea is to not add columns to it, but to eliminate columns to it through a process of refinement. Okay. This does not need any duality theory. You don't need any shadow prices. We have all the sets of columns initially, and then we start pulling them out one by one. So it's more combinatorial in that sense, rather than algebraic using shadow prices. So we have, as you now know, I think, because it has been discussed before in this winter school, we have a tool available to us, decision diagram that can represent very compactly, in many cases, the independent sets of a graph. And for this particular example graph, here is the exact decision diagram, in which that means every path from the root to the terminal corresponds to an independent set. For example, the first leftmost path here is 1, 2. That's this particular independent set, and then you don't take 3 and you don't take 4. Okay, and we have ways in previous work to compile this quite efficiently, very efficiently, in fact, in linear size in the diagram, and so we can just take that as our baseline. So if I start now to start from all columns, in this case, I have all the exact feasible paths, independent sets here in my decision diagram. How would I reformulate my MIP model? So I ask you, here's the independent sets. Give me a MIP model that gives me an optimal solution to the graph coloring problem. So in graph coloring, you need to make sure everybody is part of an independent set, every node. So for example, this is node 1, node 2, node 3, and node 4. Each one of those nodes has to be part of an independent set. So how can node 1 be part of an independent set? Well, it must be on some path from R to T that is one column in our column generation process. For example, the independent set 1, 2, that would be one possible solution. Node 2 can be also part of 1, 2, but it can also be part of just 2, 3, for example. And so the idea is here, and now I think this is a little bit of a paradigm shift. We are not looking for a single solution anymore in this decision diagram. We are looking into a collection of paths. And the other paradigm shift is the layers are not the decision variables for me anymore. Now a decision variable is for me this binary column. Do I take a column or not? Do I take a path or not? Right? And that's a little bit of a shift in thinking here compared to what we did in other works. So what I propose is to, here's the example that I showed you before. Here's one path, the 1, 4 independent set and the 2, 3 independent set. So how do we get this solution? Well, I would associate a flow variable. This has been done before in many works, actually, in decision diagrams now, very effectively, but I'm using it slightly differently here. So an integer variable through an arc is just the amount of flow through that arc. And it doesn't have to be 0, 1, because you can share 0 arcs, and there can be more flow than 1 through one arc. And then what we have to do is we have to minimize the number of paths needed to cover all the nodes. And so we want to minimize the flow out of the root that corresponds to the number of paths that we send through this decision diagram. But we have to make sure that every node, 1, 2, up to 4, corresponds to has at least one arc that it participates in. And in fact, I have here the set partitioning formulation. So for example, for the first layer, for node 1, there's at least one path. There's exactly one path with a one arc that has to go through this layer. The second layer needs exactly one arc to be picked in this solution. And this is really the set partitioning formulation of the initial column generation, but I compress it now and I express it as a network flow. Okay. This is a much more compact formulation, and it's not exactly the same formulation because it doesn't show you here because these are two separate paths, but in the decision diagram, paths can share arcs. So I can express, and so in other words, there is the same solution in the decision diagram can have multiple solutions in the associated column generation model, because there I have all the columns explicitly listed and you have them compactly listed. And so there can be some ambiguity and a choice in how to disentangle these paths in a path decomposition effect. So that's, I think, the most important change in how we approach this problem, graph coloring. Let me pause here and ask you for any questions, clarifications that you may have.
Yeah, you could also say at least one arc per vertex or something, right?
Yeah, absolutely. And actually, that's what I implemented.
Yeah, yeah.
And that's the same with standard column generation. The set partitioning can also be a set covering, and it can have computational benefits.
Yeah, I see where the talk is going. I really like the idea, Willem.
Okay, thank you. So this alone can give you some benefits over column generation, because now we have states that correspond to different things than you would have just columns in column generation. So that's a different topic. Yeah, exactly. The recombination property is what I had in mind when I think about these paths. They can cross and they can, recombine indeed. So let me move forward and explain what the challenges are. Clearly, we have exponential size decision diagrams. And you know what the answer will be? Relaxed decision diagrams, if you have visited these previous sessions as well in this week. Relaxed decision diagrams, I can scale much more efficiently, and we don't have to always go for an exact decision diagram. I can get good bounds with a much smaller decision diagram. That's relaxed. Now, going back here, this is you may think this is a network flow, which is the case, but it also has an additional constraint that you have to have one arc per vertex, per layer. And that side constraint makes this NP hard to solve optimally. So you no longer have a polynomial integer valued network flow. You still have a polynomial fractional valued network flow, obviously. It's still an LP. But I don't care too much about that. I can use an LP relaxation by throwing out the integrality condition, which is fine. And actually I did that. And I can just MIP it. MIP solvers can scale very well these days. And actually that has not really been a big drawback. But of course, that's an opportunity for further improvement if you want. So let's look at relaxed decision diagrams now. I just want to recap, just to be on the same page here, that we can have the exact decision diagram right here. And I can also merge states in the diagram that are not necessarily equivalent, so they don't have the same set of completions, that over-approximates the solutions. So the very simplest one is this all ones relaxed decision diagram that allows any possible independent set, even if they're not really feasible. For example, the all ones path takes the entire graph as the independent set, all the vertices, which clearly is not a feasible independent set. But that's fine, because we're going to relax. We can refine this, and maybe we find something in the middle that is not quite as big as the exact one, but still served our purposes for getting us a good bound. Okay. So in this approach, what we'll do, we'll start with the simplest diagram. I have just have all possible combinations of zeros and ones, the full Cartesian product, if you wish. And I would solve my flow formulation on this graph. Give me a solution. That would be the all ones path. This is a network flow solution. Every layer has one arc, and the lower bound is 1. It's a trivial lower bound. I know that, but that's fine. And we now are going to do a path decomposition of the flow. There's just one path, so it's just 1, 1, 1, 1. And I'm going to find a conflict along this path. Now, the first conflict I find will be 1, 3, because there's an edge between 1 and 3. I can identify that and now pull out that particular path. And I'm thinking I'm going to skip the following here, and I'm going to go straight here. I'm going to pull out that path and eliminate the 1, 1, 1 combination. So the first 3 edges here, 1, 1, 1, or arcs, I want to eliminate that subpath. So I do that by splitting the first state in which this path traverses that particular state. So I'm going to pull out the 1 arc here. And I'm going to pull out the next 1 arc as well. So originally I had this as well here. And I'm going to come at this state, and I can track the state information at this point. Allows me to identify that if I have 1 in my path, I can no longer take 3 because it would be a neighboring vertex. Let me just go back and actually give you the details here. This would be my first initial decision diagram. I think it was covered yesterday. The state representation is all eligible vertices that I can still add to my independent set. If I pull out the one arc because I want to separate 1, 1, 1, the first 3 one arcs, I'm going to pull out the one arc. I'm going to update the eligible set by removing its neighbors and of course the 1 itself. So I remove 3. I have 2 and 4. 2 still exists here, so 2 and 4 can still be arcs going back to the previous state where they came from. Now I'm going to separate the second one arc. Now, if I separate the second one arc, the set of eligible vertices here does no longer have 2 because I already took 2, but it also doesn't have 4 anymore. So I have the empty set. I can only have the 0 arc leaving this state. So I don't even have to actively eliminate the one arc. I can see this by construction, by compilation, if I pull out these states. That's what I do under the hood. Okay. Nice thing is, this particular procedure, separating a conflict, can only add 1 node per layer. I have n original nodes in my graph. So the number of possible nodes I add to my decision diagram is n times k if I have k conflicts. And if I repeatedly apply this, this compilation by conflict, or this refinement by separating conflicts, I will in the end up with the exact diagram if time permits. So doing this iteratively, I have this one first solution. I will pull out the first conflict. I resolve my lower bound, my network flow. I get a lower bound of 2, which happens to be optimal. Unfortunately, the path decomposition I have here in this particular example, 1101, is not yet feasible because, for example, 2 and 4 in the first path are conflicting. So I'm going to separate that path once again, even though my lower bound is already optimal, but I don't have a witness on the upper bound yet in this particular example. But if I had an upper bound heuristic, I might have stopped here. But I pulled that one out as well. I resolved the network flow. I have another conflict, 3 and 4, along the path number 2. I pulled that one out, and now I have a path decomposition that is no longer having any conflicts, and I terminate. Again, had I known that 2 was optimal by a heuristic, I would have stopped much earlier. This is not the exact diagram. And in fact, after one split, this is already the optimal lower bound. Okay, so I could have stopped here already. So what is the analysis here? I said already, it relies on this path decomposition. There is some choice here, so it's not a unique path decomposition. So you can take it to your advantage. It can maybe be a drawback. At the same time, this is quite scalable. We can, separate as many conflicts as we wish, and it doesn't really blow up the diagram. We have a control there. And what I really like, in contrast to column generation, where we have to wait until we have the optimal basis in the linear programming model, and we don't get lower bounds up to that point, here I have always a valid lower bound. Of course, it starts out weak, but it will increasingly get better. So now I have a mechanism to spend more time in this relaxation diagram and stop and terminate earlier and get some bound that's reasonably good than spending hours and hours on finding the optimal basis in LP and then finding out it may not be what I want. Okay, so this is really what I like. I get a valid lower bound at each iteration. And I also don't necessarily need a branch and bound mechanism on top of this. I don't need branch and price. If I have time and if this is a suitable enough problem or case, I might actually, when I solve it as a MIP, this network problem, I will terminate with an optimal solution if time permits, obviously. So I don't necessarily need a branch and bound on this. Of course, it will turn out we actually will need it, and that's actually future work that we're working on right now.
Willem, can I ask a question quickly?
Yes, yes.
Have you compared the bounds that you get using like a top-down standard compilation method with one of these like incremental refinement methods that you're doing? Because I mean, you could just start with any relaxed decision diagram and get it done, right? And anyway, just curious to see if you've experimented with that. Yeah,
so I did not use an arbitrary top-down compilation method up to say fixed width. What I did do is I looked at shortest paths and very, very quickly eliminated those that have feasible, conflicts. So the initial stage will do some 100 conflict separations very quickly based on shortest paths rather than on LP flows. It's super quick. That's what I do. So I do start with a reasonable decision diagram, but actually, or in this case, longest paths. Thank you, Anthony. Because the longest paths have many nodes in them, and they have more they're more likely to be having conflicts. But I don't know if this is not really matching the intuition we had from other cases. The graph really and the combinatorics of the underlying graph that we're trying to solve the graph coloring problem for they really influence where you want to go. So it's not always the best idea to start with previously known top-down compilation methods, but we can still look into that. Yeah.
Yeah, I wonder if you could tailor them. You know, typically we merge nodes based on the bound or something like this, but maybe merge them based on, I don't know, conflicts or something related to graph coloring. I have no idea.
Yeah, but actually for the routing application, actually we did do that. So we actually have a top-down compilation that's really tailored towards the application that gives you a reasonably solid first attempt, and then you start refining further along other lines of things you didn't do first. For graph coloring, we haven't done that yet. Yeah, but that's definitely something we can look into. Other questions?
So do you, sorry, Willem, do you have an intuition where mistakes they happen? Because this is not going to give you the minimum decision diagram for that width, right? So if,
yeah, it's very difficult. So we looked at the Dymax benchmark instance in particular, and they are very specific structures that are perhaps not, some of them are more practical, others are more combinatorial, and really they're more adversarial in terms of optimization. And there's often some symmetry, and so there it is actually quite sensitive to the variable ordering as well. What is the result here? So that's another topic that we studied, particularly with Anthony. So intuition is not always, what I had built up from previous cases didn't always translate to this particular problem domain. For the routing application, that was actually a little bit easier because the variable ordering at least is given in advance.
Thank you.
So this is the promise. It may work. So actually, it can work. And in this paper in Math Programming Journal, there's this theorem that says there is hope. There is a specific case in particular paths that if you have a specific variable ordering for the decision diagram, each of which gives you potentially different results, obviously, that particular variable ordering gives you an exact decision diagram of exponential size, whereas the relaxed decision diagram is of polynomial size and gives you a provably optimal bound. Now, the trick for paths is not so, I mean, in terms of the bound, it's easy because a path has coloring number 2. So that's fine. So you just, and any first split in the relaxation will give you a lower bound of 2. So this last piece here is not so difficult. That actually comes from the path. But it's more difficult is to find a variable ordering that gives you provably an actual exponential size exact decision diagram. That was actually the trick of the proof. Okay, finding this for this particular class paths, the optimality condition is that was not so easy. That's just because it has a very low coloring number in this case. But there is some hope, and actually in the experimental section, I'll show you that the hope is way better than this somewhat worst case scenario. So how do we put this all together? We'll start with the width one. As I discussed just before, I have some ways to start with a slightly bigger decision diagram than a width one decision diagram, but we'll just continue in principle iteratively refining the diagram, updating the lower bound, applying a primal heuristic to find possibly an upper bound that's increasingly better. And we continue doing this until we have no more conflicts in our path decomposition. A weakness here is that the path decomposition may not find a conflict-free set of independent sets or color classes, whereas the lower bound is actually already the optimal one. So there should exist a path decomposition, but possibly there could exist one that is conflict-free, but we haven't. But that's a possible drawback here. So the upper bound should counter that. If you have a very good upper bound heuristic, you don't need necessarily a conflict-free path decomposition, right? Because then you just care for the lower bound. The implementation is done in C++ using CPLEX as the LP solver and the MIP solver. The variable ordering in the diagram, as I said before, is quite critical. I have specific heuristic for this particular set of results I'm going to show you. It's not necessarily the best one, but it was just one that I can fix, and then we can compare the results. And there also is a portfolio approach presented at CP/AIOR earlier this year with Anthony that shows you that you can make it much more robust if you look at the portfolio of variable orderings. As I mentioned before, the default is to use MIP because it gives you an integer optimal solution for the network bound problem. But you, of course, can also solve the LP relaxation. And that gives you a lower bound that's valid. And I actually do that first until I reach LP optimality, then switch to the MIP. You can also separate multiple conflicts. You don't need one single path and that with an associated conflict. If for every path you find, you can identify possibly a conflict, put them in a stack if you wish, and then one by one you can separate them, which is very effective. And clearly we can apply an upper bound heuristic as well. So let's just first look at how strong can these relaxation diagrams be. Well, here is a scatter plot where I have the exact decision diagram size. And what I do is I use that exact decision diagram and then solve the graph coloring problem onto the exact decision diagram. The exact decision diagram contains all the columns. So it's the exponentially large set of all possible independent sets. So solving the MIP on that particular decision diagram gives me a provably optimal graph coloring solution. The relaxed decision diagram is that at which I find a provably optimal solution and there is a matching upper bound, or I have a conflict-free set of paths. So there's no branching bound here. It's just simple. What can I just iterate and iterate and iterate until I have no more conflicts or the lower bound matches the upper bound. And so these are log-log plots, and you see that clearly the relaxed decision diagram can only be as big as the exact one. But here's one case that's pretty striking, where we have an exact decision diagram that needs 1 million nodes at least, and possibly way more than that. Whereas the relaxed decision diagram can prove optimality with just 627 nodes in the diagram. That is enormously small for proving optimality compared to what the exact decision diagram size is. And so generally the decision diagrams that are relaxed and can give you provably optimal bounds can be orders of magnitudes smaller than the exact ones would have been. David.
Yeah, I mean, this is just the relaxed decision diagram you find. There can be much smaller ones that potentially.
There could be, yes, absolutely. This is a snapshot, yeah. And in fact, if we, for example, use different conflict separations, if we found different conflicts and we had or different variable orderings, we could have found possibly way smaller even relaxed decision diagrams. Absolutely. Yeah. This is dependent on the choices of our implementation. So what can we do now? This is promising. So the current best approach is actually the branch and price approach, and the best code for that is the one implemented by Held, Cook, and Sewell. There's a newer code developed by folks at the University of Twente, a master's student that did very nice work, and that implemented additional cuts that could actually improve on some of these instances further. But I didn't have that at the time of the development of this particular application. So if we compare to the Dymex benchmark, what we can solve just without any branch and bound on top of the bounding procedure that we have for the decision diagrams, it's somewhat comparable. We find more best known lower bounds than the code by Held et al. Upper bounds are roughly the same, but the branch and price code can close more instances, considerably more. If we add a portfolio approach in the variable ordering, it improves. I believe currently it's actually at 56, but this is from a couple of weeks ago. So we are approaching that. And again, this is all without any branch and bound, right? So this is purely doing an iterative refinement. It is like doing a cutting plane approach for integer programming and only doing cutting planes without any branching on top. That's what we do here. We only iteratively refine the decision diagram. But you can imagine, obviously, especially if intuition from LP branch and bound, at some point you are, especially like Lagrangian, I should say, branch and bound, at some point you should just stop trying to push more out of this bound and start branching, right? And that's a trade-off you can make, and then you can even further improve on this. And that's actually what we're looking at right now, and that seems to be quite promising. But I can't tell you anything more because we still need to finish that work. So this is quite promising in my opinion. Okay. Here is some results in open Dymex instances. As we have seen before, for independent set applications, the diagrams seem to be doing quite well in terms of representing the independent sets when there's either a high or low density. We have the same here. Well, I don't want to spend too much time here, but if you look, for example, at high or low density, the lower bound gaps here are particularly small, which is good. So at this point, I think I'm going to give you a summary. This is an alternative column elimination. Elimination means if I refine the decision diagram based on a conflict, that conflict is a column that I pull out, I separate it. So that's why I call this column elimination rather than column generation. And as I said before, we're now implementing this together with Anthony in a branch and bound scheme. And the other thing would be looking at different applications. This was the starting point, graph coloring, but it's very generic. We don't have to stop here. So the next application that we're going to look at is vehicle routing. And that's work with ZA Tang. And the benefit there is that column generation is, or the potential benefit is, column generation is widely applied in vehicle routing applications. So if we can find opportunities where column generation is weaker, what kind of instances or what kind of problem classes that the column generation does not work well on, perhaps decision diagrams and column elimination might be a feasible alternative. So again, as I mentioned before, I like very much column generation, but if you can't use it because it doesn't scale, you need to have something else. And I think we're focusing on that right now. And the first application that I want to share with you is this TSP with a drone. And before I go there, let me just pause here if anyone else has a question. Okay. And I'll start with describing the application to you, and then we're going to apply actually a similar process as we did for graph calling, because it is generic, it's systematic, and you'll see what we get. So the traveling salesman problem with a drone. It's a somewhat stylized application that mimics last mile delivery problems. We have just one truck here and one drone. In fact, you can Google it if you haven't done so already in the past, because it's been quite popular over the last couple of years. Companies like UPS and so forth, they experiment with this, in which literally there is a truck and a drone, one or possibly more, leaving the truck to make a delivery while the truck is en route. So possibly what we have here are 8 deliveries, and we start with the depot. The drone is attached to the truck. And what we could have, for example, is the truck goes from the depot to location 1, and the drone actually is en route, and while the truck is en route, is going to deliver location 2's package, and then it will reconnect with the truck in location 1. That's what this particular application would be. It's also possible to have them joined together if there's no opportunity for the drone to make a delivery on the side. So, for example, between 1 and 3 they are combined, between 3 and 4 they're combined. But perhaps here's another opportunity for the drone to split off. And then at the last section, that's again an opportunity. So that's what a possible feasible solution would look like. And of course, the benefit is that it can have shorter time to complete the entire set of deliveries, because you have a parallel drone delivery while the truck is en route. And now the durations here, if I just, for the sake of example here, assume that the truck speed is 1 unit per edge, and the drone speed is a ½ unit per edge, then we can compute what is for this first leg here, what is the total duration of that? Well, they have to reconnect, and the truck and the drone have to wait for one another. And so the total time to execute the first leg is 1, because ½ and ½ and 1 is the same. This one is combined, so it's always 1, it's always 1. And this one, we have 2 and 1. So the drone is not contributing anything to the length of that particular segment. So it's just 2. And the last one is again 1. Okay. So the trick in this particular application is that the truck or the drone can marginally increase the duration of that segment with respect to the other vehicle's duration. Okay. This is the formal definition. We have a TSP where the deliveries can be made by either the truck or the drone. The drone speed is alpha, which is a fixed constant. Typically, it's faster than the truck. And we want to minimize the total route duration. And that is so we don't, we have the make span, if you wish, or the, let's say there's no waiting and we just want to have the make span, the total duration. So when the truck and the drone are back at the depot, so the end minus the start time. Okay. And again, the assumptions here are, we cannot dispatch the drone while the truck is driving. We have to start from a location. It's not really that important, but it's just simplifying our analyses. We cannot have more than one delivery for the drone. It can carry just one package. And the last one is they have to wait for one another. In this case, the drone had to wait for the truck to reconnect. And these are the assumptions from the literature, if you wish, and also from practice. There is a lot of literature already on this, even though it's a quite new application. And the current state of the art in finding a good bound for this application, as well as optimal solutions, is one by Roberti and Ruthmeyer, published earlier this year in Transportation Science. And in fact, their approach uses branching price and column generation. It has a similar structure as we discussed for graph coloring. It's a set partitioning formulation. There's a pricing problem that tries to find new routes or new columns, and it embeds all of this in a branching price. And the nice thing is we can use a lot of this for our approach, in particular, the dynamic programming model. So in this part, I'm going to sketch what are the connections between dynamic programming and column generation and the decision diagrams, okay? And in particular, I'm going to work towards a place where the bounds will be exactly the same. As long as the dynamic program you use for column generation and for constructing the diagram are the same. And so that's what the end result will be. Column generation, now you're experts because we did the same for graph coloring, has in this case not an independent set or a color class, but every column here would represent a route, and a route is a combined truck-drone route. And it will be represented by the locations that are visited by that route. For example, here we have a feasible route and it visits every location. So this would be having a 1 at every row for every location that has to be visited, okay? So it's a really little bit of an odd representation as for column generation, but it's not uncommon, by the way, but it can be done also for TSP. You can do this. So every feasible route should visit every possible location, drop-off location. So it will be an all ones, but they not all have the same distance, right? And not everybody's in the same way by the truck and the drone. But the master problem for this particular application would still be among all possible routes, select the one, if it is integer, that covers all the locations at minimum total cost. And this is very similar to what we saw before with graph coloring. There is a hand by Samira.
Yes, I have a quick question here about the duration of routes. So we do consider this as an static, it's not dynamic situation, right? We don't consider the data that we collect as the vehicle is moving.
Yeah, absolutely. The durations here are all fixed, static, and they're fixed in advance. And of course, you can augment this application with time-dependent durations, for example, but we don't do that right here.
Okay, thank you.
Good question. And so if we had all possible routes and we could solve this MIP, we would find one route that would be optimal. But we don't want to have this exponentially large set of columns, obviously. So that's why we have an LP relaxation. By dropping the 0-1 constraint, we get a pricing problem now. So we have a restricted set of columns. We solve the LP, we get an optimal LP solution, we get shadow prices. And now the task is to find a new column, a new route that will be improving the objective function. It should have a negative reduced cost, very similar to what we did for the graph coloring application. Now the issue is here, we need to find a new route, but finding a new route is, and it should be feasible, is as hard as finding an optimal solution to the original problem. So that doesn't give us much. So in the literature, what people have proposed very successfully, by the way, is route relaxations. So you're not trying to find a feasible route, and it should be exact and feasible everywhere, but you have, for example, a relaxation in the sense that you don't have to visit all the locations. And in particular, when you look at the pricing problems dynamic programming formulation, the set of locations that you keep track of that have been visited so far are, for example, within a radius of the current location that you're visiting. And that will limit the size of the dynamic program. It will make it more tractable. But of course, you give in on exactness. But that's fine. You can actually also have infeasible routes as long as they are relaxed routes, right? So these infeasible routes are relaxed. They give you a route relaxation. And it gives you a lower bound that is tractable, or computationally tractable at least, and gives you a strong lower bound. And that's exactly what Roberto and Ruthmeyer did. And they use a dynamic programming formulation for that. And I want to spend some time on this because we will use the same for the decision diagram. So let me just spend a couple minutes on that here. So what do we need to track a route in a dynamic program and later on in our decision diagram? So we need to understand what are the customers we have visited so far. And we also need to understand when does the drone split off and where does it reconnect? And to keep track of that, we have this LC and LT as the latest combined location and the latest truck location. So we know where there was the latest time they were jointly at the location, and then where do they reconnect again. And also we need to have the time that the truck spent traveling alone, because we need that to compute the marginal increase of the drone distance. The controls are, we can either go with a truck alone and the drone will be doing something else. We can either express the drone lag or we have a combined lag. So let me show you how this works. I have a very simple graph here. I'll just walk you through one path or one solution if you wish. So let's assume we have a route 21, 22, D4, C3, C0. What does that mean? Well, I initialize my state. We haven't visited any customers so far, it's empty set, and everybody's at the 0 location, the depot. And now I'm going to take the truck to location 1. That means the drone is going to go somewhere else. I don't know yet where it goes, but the truck is doing this alone. Maybe the distance is 2. That's fine, that the weight of this arc will be 2, and the distance traveled by the truck alone is 2. It also moved to location 1, and the set of customers visited is 1. Now I'll take number 2. T2, the truck is still on its own and the drone is still going somewhere else. It's fine. So the set of customers visited is 1, 2. And maybe this, by the way, is duration 2. So we can have a weight of 2 for this particular transition. This is the set of customers visited so far. Latest combined node is still the depot. The truck is at 2 and it took 4 time units to get there by the truck alone. And now we're going to reconnect with the drone. And meanwhile, the drone in hindsight has visited number 4. So we close the segment, if you wish. The drone goes to 4. Maybe that takes time 3 in total. We have visited 1, 2, and 4. The truck was the latest combined location was 0. Now it's 2 because we updated that. The latest truck location was 2. It's still at 2. And now we reset the time traveled by the truck to be 4. But what is the weight for this transition? What is the duration for this transition? What does the drone contribute to the route length? Well, that's the marginal increase of the duration. And in this case, the truck took 3 time units and the truck that we kept track of was 4. So the increase is actually 0. It's the minimum, the maximum of that difference with 0. Okay, and that's how we keep track of this route, and we can complete the solution by 2 more combined segments. Okay, so this is a very nice way to express a dynamic programming formulation. What can we relax here? Well, we can relax the customers visited so far. If we shrink this set by a relaxed set, for example, we don't keep track of everybody, but only those within a certain vicinity, we can have a more tractable dynamic program, and it will be a relaxation, and we would allow repeated visits, for example, or not visiting everybody. So this has been embedded in the branch and price by Roberti and Ruthmeyer very successfully. But we can use exactly the same. I don't know, I think so yesterday probably you also discussed how dynamic programming models in general can be used to compile decision diagrams. If not, we can look at this earlier work that we did, but we can actually use the state transitions that we use in dynamic programming, similar to a state transition graph there, to compile decision diagrams. So if we were to do that, we would have the exact full state transition graph. It would be enormously big. If we have no node relaxation or state relaxation or route relaxation, it would be exact, and we can find the optimal solution. But of course, that's not tractable. But if we were to apply, for example, the NG route relaxation, we would have a smaller decision diagram, and maybe it's tractable and we can solve it. We don't even need column generation then. I don't think it will work, but we could potentially. What we are going after is a different route relaxation. One that's not given by the NG route relaxation, but one that's given by the decision diagram relaxation, by merging rules. And so it will be different, but it may be effective. And let's show you what this node merging looks like. Here are 2 paths in the diagram. There may be other paths, but I'm just pulling these 2 out to illustrate what node merging could be done here. You can, in principle, go in any layer and merge 2 states. but doesn't always have to be effective, right? So if we merge these two in this layer here, how would that influence the decision? If you interpret what's going on here, these two paths, T1, T2, and T3, T2, they represent subsets of segments in which the drone is doing something and the truck is on its own. They go in different directions, and they may be radically different, in fact. And that's very difficult to get any structural handle on the decision diagram. What would be better, and I tried to convey this to you, that you have these segments, these close segments where the drone splits off and then reconnects. If you can somehow get that in order, that'd be a better combinatorial handle on what we can control in the diagram. And what I mean is that let's look at latest combined nodes and latest truck nodes. Where were they together? For example, in this particular layer, the latest combined location was 0 and the latest truck location is 2. Same here. And you can see in this graph, either the truck went from 0 to 2 via 1 or via 3. But it's the same, in a sense, a similar segment. The drone actually went to 4 in both cases, but it doesn't have to. But at least the number of steps is the same, so the number of layers that has been traversed is the same. And we have a better handle of combining these things. So it gives you a little bit more structure in merging. So that will be our merging rule to get started. So when we do the compilation for the relaxation, we will only merge nodes that have this segment idea in which the latest combined node and the latest truck location, I should say, latest combined location and latest truck location is the same. If we merge those two, one benefit is clearly that we can keep this 0, 2 the same because they are the same in both nodes, in both states. So what would be the set of customers visited so far? Well, we look at the literature, and the thing we want to have is a relaxation. So we don't want to take the union of this because we would allow states and paths that are not in the diagram so far. And by taking the intersection of the two sets, we have a relaxation, a proper relaxation. So in this case, we need to have a 2 visited by both paths, if you wish. Now, what is the time spent by the truck? What is the 2 and the 4 and the 2 here? How should we combine those two? What is the merging rule there? Well, you may be tempted to take the minimum because you want to be relaxed. But the only way that we are using this information is to compute the marginal increase of the drone. And for that, we need to have the worst case scenario. And for that, we take the maximum of the 2. That's how we get to this merging rule. Okay. So it may seem a little bit counterintuitive, but this is how you get the proper relaxation. In other words, this is a application-dependent or dynamic programming-dependent merging rule that we apply for top-down compilation to create an initial relaxed decision diagram. So how can we do this? Well, we only merge states that have the same segment structure, so in which the latest combined location and joint location, this LC-LT pair, are the same. So we can, at each layer, partition the nodes in buckets. We can limit the size of each and only keep the best ones, say the M-1 best ones in terms of shortest path we keep, and the rest we just merge. You can count how many of these buckets there are, what their size is, and the total relaxed decision diagram has this size cubic in N and then a constant M in terms of the bucket size, which is clearly smaller than N, the number of locations. This is a very nice polynomial-sized initial relaxation. And this answers David's question of, can you start with something more meaningful than just arbitrarily separating conflicts? This is a tailored way to get an initial decision diagram that is better than just starting from the all ones path, if you wish, in the graph coloring case. And then so this is what we do. So we use the state information is still the same state information as the dynamic program had. It's the same Roberti-Ruthmeyer dynamic program underlying this, but we don't have an NG root relaxation. We have a decision diagram relaxation. That's quite different. But every state here is the same for elements. Okay. And then we apply the machinery from graph coloring. So we have an integer network flow formulation. We still need to have paths here. So every column is a possible route. It's no different here. And we try to find one that is optimal. It's NP hard. What makes this NP hard? Well, the integer condition on the edges. So we can make an LP relaxation which is tractable and which is fine. What also makes it hard is this constraint, that every customer is visited once. In other words, across, for example, think about location 1. That means it can be visited by T1 or by C1, either by the truck alone or by a combined route. So this constraint would be the flow through T1 and C1 equals 1. So at least exactly one of them should be visited. If we relax that in a Lagrangian fashion, for example, we would no longer have that constraint that makes us all NP hard, and we have a Lagrangian relaxation. And then we can just use a shortest path method, because and it will be integer as well, right? So that's two different ways to solve this constraint network flow in a relaxed fashion. We can also use an integer program, but this is going to be a little bit more complex in the graph coloring application. So we really want fast LP or relaxations. Now, the nice thing is, if you use the same dynamic program for either column generation, the Roberti-Ruthmeyer approach, say, or the Lagrangian, or the LP, it's all the same lower bound. They all will converge to the same lower bound, okay? So that's nice, because we know that we cannot go worse if we have enough time to do this, all right? And then we may be better. And in fact, we can go beyond this set partitioning bound. So we have a decision diagram. We can do more than we can do with dynamic programming and pricing, for example. But you could potentially transfer these ideas also to dynamic programming, by the way. Because we have this initial relaxed decision diagram, but there are still conflicts there. We just had this n-cube size relaxation. Let's inspect the solution for conflicts. There may be conflicts because the objective function was not appropriately represented, because we have a relaxation there as well. Maybe there's repeated visits. And we can separate those conflicts. And that allows us to go beyond the set partitioning formulation for the standard column generation master LP. So by further refining the decision diagram, we have a chance to go beyond the column generation lower bound, okay, which I think is quite interesting. Of course, it takes time. So the idea is this: we have our initial relaxation. We compute the lower bound like we did in the graph coloring case. We refine the conflicts as we did in graph coloring, and then we continue until we either have some stopping criterion or we have no more conflicts. We can, of course, as before, embed this in a branch and bound. We did not do that yet. So what's the experiments here? We have two variants. We first look at the flow, Lagrangian, and then we have iterative refinement. And we want to compare to what the column generation model would do. And we re-implemented that column generation model so that we have a very clear comparison between the same DP model from the implementation that we have for the decision diagram, as well as the column generation. In fact, the column generation uses many tricks in terms of dominance detection and other things, and the NG root relaxation, in fact. So it's not really having the same DP model here. We have the best relaxation we know from DP versus what we have in terms of the decision diagram relaxation. And this graph on the left shows you for 15 locations. These are, by the way, very small instances compared to what we're used to in traveling salesman problems or with VRPs, but they are very challenging applications. And here's the optimality gap over time. And this is, I want to show you the following. So the NG-root dynamic programming pricing problem and so forth, and the master problem takes time to compute. That's 100% time. Until that time, you don't get any valid lower bound. But the decision diagram does give you a valid lower bound. And in fact, the Lagrangian approach in this case finds the same bound quicker and actually can go beyond it by further refinement of the diagram. Okay. Now, it doesn't always work like that. In this particular case, number of locations 20, the Lagrangian approach approximates the column generation one, but it doesn't go beyond that yet after this much time. Okay. Let me just look at this over more locations, 15, 20, and 25 locations. This is a box and whisker plot for the NG root column generation LP. then the flow model, and that's the standard LP relaxation, and then the Lagrangian solving of that particular model. And you see that, you know, the bounds we get in terms of optimality gap are really comparable when we fix the time to the time that it took dynamic programming and column generation to solve it. So that takes 100% of the time. We give the same time unit, the same time to the other two approaches. So within the same time, this is what their end result is. So this is comparable in terms of quality. Nice thing is that in terms of dynamic programming formulation, if you were to compare the states of the NG root with the states of the decision diagram, we use way fewer nodes or states in our decision diagram than the associated dynamic program, which has been trimmed for the NG root. So that's another interesting observation. If you go beyond 25 to 30 locations, we can no longer apply column generation in our implementation, at least. And so that's really where we have to do something else. So now we take another LP relaxation, again from a different paper from Roberti and Ruthmeyer, that gives us at least some lower bound. But you see that that's this blue box here. In terms of optimality gap, the decision diagram bounds are much better than that one from this MIP model. So this shows you that where column generation is running out of time, the decision diagram approach can still get you bounded. They're pretty good and can be actually better because you can go beyond the column generation massive problem LP. So that's the conclusion of this routing application. Similar to graph coloring, it gives you an alternative column elimination relative to column generation. It's reasonably good. I think for graph coloring, there's a lot of promise for routing actually as well, because now we can scale this up to larger instances. Next step clearly is to embed this into a branch and bound and to look at other routing applications as well. So I think I'm a little bit over time, maybe 1 or 2 minutes. So, but I think it's almost perfect. So David, back to you.
Excellent. Willem, thank you very much. Everyone, a virtual applause for Willem. I think it's a really good idea. And I think kind of a very, very different approach to the column generation type of solving method, which I think is obviously very promising. So thank you very much. Any questions immediately for Willem? I'm sure he can respond via email later on, but if anyone has anything in particular, please go ahead. We have a 15-minute break until the next talk, but we can just stay here and hang out or do whatever. So if you have any questions for Willem, let us know.
There were 3 hands, but somebody eliminated the hands.
Oh. Maybe they gave up. I don't know.
Michael.
Hi, Willem. Nice to meet you. Nice to see you all. By the way, thank you very much, Andre and David, for organizing this winter school. I enjoy it a lot. I cannot participate in all talks, but this one I was particularly keen on seeing. So you mentioned the branch and bound. So do you plan to implement your own branch and bound strategy, or do you plan embedding it using callbacks into a solver? Because you will certainly change the space of variables and things like that.
We plan to do this. Actually, we did do this already with Anthony. He did the work, in fact, in our own solver. There's no need to use any other environment. It's quite simple, in fact. I mean, abstractly speaking, you have a queue of states and you pop and you add. That's it.
Okay, so you basically use maybe a MIP solver for solving the LP relaxation, and then
yes,
and then do the branching on your own and always solve a new fresh LP.
Yeah, I knew that question would come up, and that's a very good question. And we can try to make it more incremental by, for example, saving the basis and keeping a thread open. I don't think that has happened yet. I must say that's not, I think, the computational bottleneck here. We are really at the early stages. So what's most important is the branching heuristic. And this we use the Zykov branching strategy, the same that was used by Merotra and Trick and others as well, where you pick 2 nodes that have either the same color or they don't. So you can either contract the nodes, or you can add an edge in between them. But which of those 2 nodes do you pick? And that's not straightforward. That has a much more, for where we are right now, that's much more important than making it incremental in terms of LP solving.
So thank you very much. And then there's one more, let's say, question or comment. So can you relate this also to for example, when you look at the NG path relaxation or in general state space relaxations, there's also a technique called decremental state space relaxation, which is kind of also refining the state space. Did you look into the connections of your approach to that?
Yeah, we didn't do that in detail. For the empty route, I think it is rather clear what the difference is in what we do. But there are clearly different relaxations of how you would compute dynamic programming state space, if you wish. So I mean, it's a good question, but we didn't go into much depth on all the other alternatives that are out there, which I think is definitely worthwhile.
Okay, thank you very much. Great talk, by the way. Thank you.
Thank you.
I mean, there's always also the question of how long you spend getting the bound better and everything before you branch and such, right?
Yeah, so there's different strategies, and this is still under development.
Yeah. Cool. Everything is amenable to learning, of course, right? So learn how often you should train, and which nodes you should merge, right? You can also just test a bunch of them on a particular class of instances or something like that. So yeah, cool.